Yeah, I think it took me a bit to figure the calculations out, but I mean, once I did, yeah, I wasn't, once you get the calculations, there's like no discussion to have, because like all it is calculations.
Yeah.
So like there's nothing really to talk about necessarily, so it's pretty nice in that front. Yeah, so I don't know, it was shorter than and it's just, yeah, it was, mine was only 6 pages.
It looks like your boards without holes.
I didn't know you did that.
Yeah, and we didn't have analytical class yesterday either. Yeah, the lunch area, we didn't have that either. Did you go?
No, that's the thing. I gotta make it run. We're all.
Oh, you've already taken it? Oh, okay. Got it. Yeah, we didn't have that class yesterday either. So like now we don't have this. So this is funny. Yeah.
Oh, that's. Thank you.
Yeah.
Hello again. What are your plans for this evening and weekend? Well, this one should be experimental option of doing homework is MATLAB only. And if you join the lab tonight, you can complete everything. So, huh?
That's what I like to hear.
Me too. I hate homeworks. I don't know why they need it, but it's tradition. You see a little small font of making animated movies and uploading them to YouTube. So partial responsibility on this decision is on Morgan, right? And learn from him how to make movies. It is a part of the homework. And I'll distribute this code if it was not distributed by Dr. Khan last time. I'll just send an email. So we go over the, we will not spend time right now, but we are looking a little bit forward. The code illustrates the material for like coming Monday. And, it's always a challenge to match labs, homeworks, and then class material. And this one will be for the next time in a week, right? Okay, going back, close your eyes, take your popcorn and relax. I'll tell you when to wake up and when there will be something important. And it will be by the end of the meeting, like last 5 minutes. Who we are and what are we doing? Oh yeah, good. So we are targeting to.
We talked about semiconductors.
Yes. Why? Why not molecules? Or like hydrogen atom, which seems a little simpler than semiconductor from general logic.
That's one-dimensional?
Yes, because we want to pump our mathematical muscles on a ramping scale, and doing three-dimensional even hydrogen atom is too challenging. And there are simplified models for semiconductors and conjugated polymers that we are already ready to take. So you may not realize, but you have already solved the equation. You did solve the equation that describes particle in the box, right? Which means electron in conjugated polymers or in sandwich between semiconductor between the electrons. When you were doing problem number 5 in the last homework, remember unknown function equals sine plus cosine with unknown coefficients, and you were matching boundary conditions. So in some sense, you already covered the material of the next chapter. You, from mathematical point of view. Now we need only to interpret it, and I'll probably show once again the key to this problem so that we refresh and get some numbers. So we are looking on class of materials, molecules, objects where electron has two regimes: forbidden regimes and on outside of the box, and allowed regime inside of the box. So it gives the simplest possible potential, right? So zero potential inside, or it works as the free particle and it just doesn't go across the box. Which scientific questions can you pose to this problem? Of course, this problem was solved many times, and we cannot. It's not likely that anyone of us can publish it and praise it as a big achievement. But if you would approach it for the first time, and sure that no one else did, which questions can you pose to this scientific question? If you know that electron moves along conjugated bond in the oligomer, or it is a sandwich where dielectric is enclosed in insulators, and you want to find some trends in motion and quantum states of electron in this system. Just give some ideas, crazy ideas, are fine. We'll see them. Or let's maybe, there are two ways: general curiosity and random number generator for ideas, and another just look on not what we need, but what we can do among the tools that are at our disposal. What can you do? Which tools we got? Which mathematical tools did we get in this course for description of wave nature of electron?
Sure.
Which one? Yes, time dependent and yeah. So time dependent is for predicting future. What will happen if one removes system from equilibrium, it kicks it and looks how it responds to external perturbation. And time independent, which questions does it answer?
Answer like location.
Location, yes. Shape of like probability distribution. Good. And what else? It's more for the time, but what else? What are unknowns in time independent Schrödinger equation? Yes. So, and why do we need energies? Yes, you are inside the course and you already see internal logical connections. But for outside of the course, if we are, not we, but if you can consider an engineer who wants to hire us to help to fabricate a device for light emitting diodes or TV or whatever, transistors, or I don't know, sensors for gas that will flash, or by imaging, any applications of like molecules, semiconductors, polymers. What can this engineer request from us?
The way to make it.
And I'm trying to browse in the space of my own thoughts and invite you there, but it's not quite clear, but I have general direction. So connection between energy and engineering of materials.
Wavelength?
Yes. Can you open this idea in more details?
They want a specific color or something that corresponds to an energy.
Or brightness. Or
Something like that.
So what's the connection? Color, wavelengths, and energy. Please educate us.
Absorbance.
Okay. So it absorbs a different
Specific area.
wavelength, specific color.
Each energy has its
And it may emit a specific color.
Yeah.
Now, what's the connection between color and energy?
Frequency.
Yes. So if we know solution of time independent equation, we know energies of states. And light absorption and emission is transition between such states. So if you know their energies, we know their offsets. And this energy of the offset will give us frequency at which the system provides light absorption and emission. Okay? So it would be really good if you catch some trends of energies for electron confined between walls. Good? But it is too general, like applying to federal grant. Supply me with everything for 5 years and I will find something. It doesn't work. It needs to be more specific. When we were looking for electron in the free space, what was the minimal energy available for the cell? Huh? If the momentum is 0, and energy is momentum squared over 2 mass, 0. So it was possible that electron has 0 energy, right? And it goes very nicely with your intuitive feeling. Right? I'm not moving. I'm about to oppose. My energy is 0. Question. If electron is squeezed between walls, would it be possible to have 0 energy? Between walls. Like in a free space, it can go anywhere. In the walls, in the particle in the box, which represents either oligomers or sandwich of the semiconductor dielectric, it's squeezed. It cannot go across the walls. We would be available to have 0 momentum and 0 energy. You are right. But we do not have proofs for that. The intuitive idea that if it is confined between the walls, it kind of reflects from them and cannot be at absolute rest. So there will be some minimal amount of motion, and even if in average it doesn't move anywhere, it has some kinetic energy. Right? Now the question how this kinetic energy of the lowest quantum state depends on the size, on the length between walls. How the energy of the lowest quantum state depends on the distance between walls. Yeah, if you can answer it philosophically without solving mathematics. So, in the infinite wall-less space, 0 energy is available. Therefore, if we increase the length, the energy of lowest state should decrease, right? Yes.
The lowest.
Lowest state, yeah. So now we do have a hypothesis, which we just generated from scientific intuition, and we can apply mathematical muscles to prove it. Right? So we hypothesize that if electron is squeezed between walls, the 0 energy will be unavailable for it. But the value of this energy will be sensitive to the size of the box. Okay? So it is motivation for our efforts and for suffering not. I always promise myself that I will be writing during the lectures, but it's so tempting to show slides that were written before. I know it's very tempting then for everyone in class not to write. But I don't care how you do, but when I was in the undergrad, I was trying to write as much as possible because it's additional channel of memory. But as promised, lean back and relax. I'll tell what are the important things. So between 0 and L, we set up X axis. In here, electron can move, and walls there are so much infinitely high that it's just forbidden to go there, right? And then we do formulate the, we want to say solve Schrodinger equation, and we want to formulate Hamiltonian, which will be kinetic energy, secondary, and potential. So potential will be either 0 or infinity, right? So how do you solve such, what we have to solve and how we are solving this problem? So our local technical goal is to solve time-independent Schrodinger equation for particle in the box, where size of the box is fixed, and we need to have some protocol to convert this scientific physical chemistry problem onto language of math, differential equations. So it's there is one independent variable, there is a second derivative, and we even can get some general solution, right? If there is a function and linear combination of derivatives, the solution should be searched in form of exponential, generally, because derivatives do not change the shape of exponential. And the whole business of differential equations is just finding powers of the exponentials and factors in between, if it is linear. Right? No? Prove me wrong. But what is, so it looks like if we have this differential operator and the unknown function here, that solution will be something simple, similar to exponential. But what are the additional challenges, additional details that we have to address? How do we address presence of the walls? Do we have probability to find electron in the walls? Not inside the box, but outside of the box, in the space where energy is infinitely high. What's the probability to find electrons there? Yeah, like I'm not a mount climber. I do not have enough energy to climb there, so therefore I will stay at a low level. Right? So 0 probability to find me on the top of the mountain. Same for the electron. So, and I'm even not going to try to climb. So as soon as I approach the edge of the wall of the mountain, my probability to be there will be 0 because I'm not going to climb. So on the points where independent variable is either 0 or L, so left or right edges, the unknown function must be 0. Okay? How do you already did it in the homework, but how do you call it in the differential equations? There is a colloquial name for such class of problems. I know you can be distracted by this ugly slide, but just let's talk rather than watch the initial value. If you set up only one edge, and typically if you do not know what further, it's if the independent variable is time, initial value. But now we know the begin and the end, and it is more space rather than time. So there are edges, there are boundaries, and there are conditions. So it's if you look in like text book on differential equations, you need to look for boundary condition problems, right? Oh, it is written. So I invite you to sleep most deeply at this slide. It's mostly boring. Do not look at it. So generally, linear differential equations have solutions in form of exponential with unknown coefficient. if we take Schrödinger equation and plug in there this function form of exponential, now I know why we completed in time. In previous years, I was trying to write it and it was expanding. So, second derivative of exponential gives square of this prefactor, and then we can cancel exponential. And then we get an equation that this unknown factor in power of exponential equals, remember this minus comes from definition of momentum, minus I h bar ddx. So if you set up this equation and want to solve it for alpha, for this unknown coefficient, you'll find that it will be square root of mass, energy, divided by time constant, and here will be square root of minus 1, which will be imaginary. So the from this consideration, we can say that factor that comes here must be imaginary unit times real number, or that factor here must be imaginary, right? Those who didn't get invitation to sleep may agree. So we have imaginary unit times real number here. Now a little bit more thinking and general consideration. If you have exponential with imaginary unit times real k times position, it's nothing but plane wave, our favorite, the only function that we know by now, that is a wave function. And then by adding together plane waves, we can construct the Gaussian, right? Plane waves can be moving forward, can be moving backwards, right? So no mathematical proof, just common sense. If you have a box that is set to rest, in average contents of the box cannot move anywhere. In average velocity must be 0. But if the electrons there can move either left or right, it means it is the equal proportions of probability going forward and backwards. So it should be summation of plane wave going forward and plane wave going backwards with equal coefficients. Right? Make sense? So that in average it will move nowhere. And now we may want to take this general form of solution for time-independent equation, plug it into there, and find coefficients here and the powers of exponential. Keep slipping, it's not important here. Just technical results. Everyone is welcome. Oh, okay. So, we are, hopefully we are getting new friends through this course. So we got acquainted with Schrödinger, Heisenberg, who else? Hermit, Euler, right? So what he taught us, and Gauss, right? So what do we learn from Dr. Euler?
How to change an imaginary exponential into a
Sine and cosine.
yeah.
If you add together two exponentials that accumulate phase in opposite sides, instead of imaginary exponentials, we can get sine and cosine, where all imaginary nature will just pop up as an imaginary factor in front of sine. So we are looking for solution in this form. Coefficient in front, C plus in front of positive, C minus in front of negative. Now, replace each of this exponential according to Euler equation. So it will be cosine positive factor times z, imaginary unit sine positive times z. It comes from this exponential, right? And here, second exponential will be cosine of plus kz, because cosine of plus and minus is the same. It's even function. And here we have minus, because sine of minus kz will be minus sine, right? And now we see that this function consists only of two independent functions, only sines and cosines. So this are the same, and these two are the same. So we can combine them together. Combine together all sines and combine together all cosines. Then we will have linear combinations of the C plus and C minus coefficients. So this summation of cosine and sine is nothing but a general form of two plane waves coming to each other, but we superimposed them and mathematically practiced the Euler equation, right? What do we do next? We have two kinds of unknowns. We do not know the value of k. We do not know the value of c plus c minus, but we do know the size of the box. Right? And we expect that differential equations often have more than one solution. So basically, the general solution is already available. We just need to match boundary conditions. So we plug this equation into condition when z is equal to 0, and then function must be equal to 0. And then we plug the value of independent variable to equal to L. And then the function also needs to be equal to 0, right? So, and from these two equations, one will be able to find both this power, this rate, and the coefficients. In the homework number 3, problem number 5, we did this exercise. You all have either successfully completed or participated in grading, so it shouldn't be very much of novelty. You need a little bit translation. So this part was, I think, named B or A, and another one, this IC, was called B, right? Do you see any flashbacks? So the part in front of cosine was found to be 0, which means that C plus is equal minus C minus. And the front of sine was obtained by normalization later on. So from your homework, we can discard this part and keep solving only for sine under the condition that it should be 0 when z equals 0 and z equals L capital. Right? So if you plug 0, it's trivial, and if we plug the limit, then sine will be 0 if the unknown times L equals n pi, where n is any natural number, right? So it's your high school trigonometric functions. In fact, for this problem, we do not need to take differential equations. So from this, and I'm a little swamped in notations. A couple of slides ago, we were calling this like K. And it is not my problem, it is your problem. You did it in your homework, right? And you know how successful you were through grading process. So you are getting the values of this rate in front of independent variable, which is n pi over L. So it does depend on the size of the box. Right? And one can get the coefficient from normalization. Good. Keep sleeping. I'll tell when to wake up. You can keep, you can take notes, but you don't need to wake up for that. Right? It's automatic skill. So we already discussed that in free space energy is 0, and our goal is to find minimal possible energy. All our efforts are targeted right now to answer this question. Therefore, we are suffering this differential equations. And intuitive answer that it will be inversely proportional. So if L is infinite, then the energy should be 0. But by now it's yet hypothesis. But we are going to bring meat to this bones. Okay. There will be something even more important, but if you are debating whether to sleep or wake up, it's better to wake up and follow. So the top line is the answer that you have obtained in your homework. So how does the orbital, how does the wave function for particle in the box look like? Schrödinger equation gives two sets of solutions: eigenvalues, eigenenergies, and eigenfunctions. And those are eigenfunctions. So it will be sine functions, where in front of independent variable you have n pi over size of the box, right? And there is a normalization function. What will be the, what is our scientific goal? What are we going to find? Yes, yes, lowest energy. So if we know the wave function, we can find energy. Right? There is, even if it is not eigenfunction, there is a bridge from abstract wave functions to observables, just putting wave function star, operator wave function, and integrating. So as soon as we know wave function, we can always find observable energy. But here we can do a little simpler. We do know that there will be no potential energy. There will be only kinetic portion, right? Because where potential is high, there is no probability for wave function. And now I'm inviting you to follow the simple hand-wavy mid-school level logic. So this is wave function. The factor in front of independent variable is, you can call it wave vector or just rate. And this wave vector is connected to momentum by multiplying it over time constant. Good. No one throws tomatoes at the speaker. Yeah. Okay. Now, if you do know the momentum, one can write down the kinetic energies, momentum squared over mass. Right? And one can replace this momentum with this wave vector. So one constant wave vector squared over 2 mass. It's kinetic energy. But the wave vector is not arbitrary. It takes the discrete values. So instead of k, here we are plugging this discrete values, integer number times pi divided by size of the box. And then we get energy is one constant, two masses, and instead of K it will be n square pi square L square. Right? Catch me if you can on the consistencies. It's a little quicker than standard way of finding bracket and operator in this simple case. In the future, as soon as we know the function, we will just use operator and convolution. So if we want to answer our scientific question, how the lowest energy responds to the size of the box, to distances between the walls, we should plug number 1 instead of n, right? And write energy for n equals 1 will be 1 constant squared, 2 masses, pi squared, L squared. How does it depend on size of the box? Inverse to the square. We were guessing that it will be 1 over L, but we're not too far. It is a very strong statement. I'm going to offer a little summary of what we did in the chart that helps memorization, and then we will discuss how to interpret this result. So this is the simplest application of quantum theory. If you are not decided which career path you select, like work at bank, or inherit control over company, or like work in industry, or go to academia into research, or maybe it's not everyone likes it, but there is an opportunity to teach at college. And then if one needs to squeeze quantum theory in like one meeting, it is this one. So this is the simplest part of quantum theory that is possible to deliver to someone with only high school background without any calculus, right? Because like you just plug in and get important conclusion. So if we want to look on it and analyze it, then I'm still having problems remembering immediately all factors one after another without a cheat sheet. But one day you may need it for analysis. So what is there? How to interpret it? Now we are, please wake up, and we are speaking at the language of kindergarten. I apologize for the simplicity, but you may benefit it later when you need to deliver it to someone else. So energy of quantum state number n for the particle in the box. There are constants like pi, 2, and Planck constant. What is it? Planck constant is in standard system of units is like 610 to the minus 34, something really small. Which means these effects will be observed only on atomic or nanoscale. If you look on scales of the real world, we will not see this discretization. So there is a Planck constant. It's essential quantum effect. So next factor, it's inversely proportional to n. We are talking about electron because we are in. I think most of us are in chemistry department, and we are looking on molecules or positive ions and negative electrons. But the laws of quantum theory are more general. Instead of electron, one can use different particles. For example, in some reactions, proton is getting transferred, and it exhibits quantum properties. So if we use something different than electron, one needs to modify the mass. And the larger the mass, the smaller is energy, and the smaller are quantum effects. So that's increased. The next factor is n. So this first is non-linear, so the offset between energies will be increasing. And even more important, it is discrete. So from now on, we all are allowed to use word quantum. Before, we were not authorized, because electron in free space was permitted to have any momentum and any energy. It's like a reckless driving on highways in Germany. You know that in Germany there are no traffic signs. Well, there are traffic signs, but on highways there are no speed restrictions. You travel as you travel as quick as you can. It's your responsibility, right? Am I in time? Yeah. But here in this problem, you see that both momentum or whatever square of this wave vector and energy do have discrete features. It's same as on the highway. It will be told you are allowed to travel 10 miles per hour or 20 or 40, but any value in between is forbidden. And the policeman gauges with the device and looking, oh, you are a little slower or a little quicker. No, ticket. So only discrete values for motion, only discrete version values of energy. So this discretization is referred to as quantization. And typically one uses the word quantum as an energy of transition between the states. We are going to quantization, and therefore it is quantum theory. Quantum is synonym of discretization. And here's the answer on your scientific question. How does energy respond to change of the size of the box? Good. So if you decide that for your career you need to teach at college, you are ready. If you want to work at industry, then before this minute, Alyssa was mostly educated in emission of confined quantum nanostructures. Look at her, applaud her, but starting from the next minute, you catch the same level. So, in oligomers or in semiconductors, which are pieces of confined in space where electron can go across the wall, the color and absorption is good, is important, but most industrially important is emission, because most high quality TV panels are, you notice, like quantum.tv. Did you notice? If you go to Best Buy and look for options for TV sets, and there are like organic light emitting, and there are quantum
OLED.
Yes, and there is a quantum dot LED, and quantum dots are they're more expensive, but if you judge their quality by human eye, you see it is brighter, deeper colors, and so it is based on small pieces of semiconductor of different size. So one can have the A material of the same chemical composition, but carved in small pieces with different regime of confinement, with different size of this between the walls. Right? What Alyssa is exposed are quantum dots, or they're spherical. Here we consider right now only flat things, but the principle is the same. By changing the size, you can keep the same material, same chemistry, but very different properties. So it's beautiful, unusual, and this idea of controlling the color with keeping chemical composition but changing the thickness of layer is the essence of the nanoscience, the nanotechnology that is being a buzzword for the last, I don't know, 20, 30 years. So it is this idea that you keep same chemical substance, but you control programs because of controlling the size. So in real materials, the energy between like occupied, unoccupied orbitals, so-called gap, is fixed if it is infinite like chunk of material. But if we take a semiconductor of smaller and smaller size to this gap that determines color of like chunk material, there is an addition that comes from your accomplishment in the homework, from what we did today in the lecture. So there is an addition of energy. So if it is free space, it's just a little above zero. If it is a real material, it is a little above of the bulk. There should be no energy. So that comes here. So a little addition to the fundamental band gap. And by tailoring size, one can tailor the color. So the example for material most popular, most cheap semiconductor is silicon. It's like sand is silicon dioxide, silicon is crystal lead. The bulk is 1 eV, and if one carves it to the size of few nanometers, it comes to this. This is infrared, and small pieces become bright in the like yellow, blue. One can control the color. So people refer to the word tuning, tunes the image. So by request of having material requested wavelengths for absorption and emission, one can engineer material with desired characteristics just by fabricating size, which in chemical lab you can do nucleation for longer time. And if it is epitaxy, you just do chemical vapor deposition for also for longer time. Thank you for questions, interest, participation in the discussion, and I look forward to see as much of you as possible tonight, 5 p.m. I don't care, but it is your interest to have laptops with MATLAB.
In that constant struggle with getting out of space.